notation is used for summation problems. Okay, so this fancy E right here, which is one of my more favorite math symbols. If it's typed, I don't like writing it because it's hard to write pretty, or I don't write it very pretty. Yes, there's a Greek letter called sigma here, and it is going to be used for summations. So this will be, we did do some of this in pre-cal. Did we do some of this in pre-cal with you guys? We definitely did not use the funny letter, but I don't know if we did with you guys or not. Sequences in series, we did a little bit of it. It was like the A sub n. It was like where you add things together. So this is related to that. This would be, I think we didn't do series where you have to like add all those together. We did do the sequences where you had to do like A sub n equals 2, A sub n minus 1 stuff. So this would be if I want to add up all of the numbers there. So for our summation right here, we will have the funny letter. That's telling us we're going to add all this stuff up. Underneath the funny letter, we will have the I equal to whatever number they put here. That is called our index of summation, and it's our start value. It's the number you're starting at. Okay? They don't always use I. Sometimes they'll use J's and K's. It could be a different letter besides I right there. Our textbook uses I, or the old textbook used I a lot. Seems like I see other letters more often these days for that. N, the number on top, is your upper bound. It's the number you're stopping at. And then this A sub I right here could be anything. It could be several different types of expressions there. So let's look at a really basic example. Okay, we have the summation of I from 1 to 6. Okay, so our variable here is just I. So what this tells us we would do, if we want to write this out, is we would plug in 1 for I, which would just be 1. And then we would plug in the next number, because we're going to go from 1 all the way up to 6. We'd plug in the next number for I, which would be 2. And we would add it, because the sigma notation is telling us to add it. All right. Then we'd plug in 3. And then we'd plug in 4. And then we would plug in 5. And then we would plug in 6. We would just add all the numbers from 1 to 6 is really what that is asking you to do. So whenever you do that, let's see, we got 6, 10, 15, 21. For that would be our answer. Okay, let's do the second one here. This time we're doing the summation from 0 to 5 of I plus 1. So that would look like this. We would plug in 0 for the I, so we'd have 0 plus 1. And then we'd have to plug in the next number, 1 plus 1. And then we do 2 plus 1. And 3. Oh, forgot my plus sign right there. Plus 1. 4 plus 1. And 5 plus 1. Okay, now, what's this going to equal? 21, same as last one, all right? Because here we're just going to have 1 plus 2 plus 3 plus 4 plus 5 plus 6, which will give us 21 for that one also. So both of those summations have the same value. If you really analyze what's happening, you can kind of tell that they're going to have the same value because our start value is 1 less and our end value is 1 less. But we got the plus 1 there that just basically adds 1 to the value when we plug it in. So it ends up being the same for that. Okay, questions? Okay, You guys try the next two on your own. They use a different letter on number 3, but that doesn't really change anything about how you do it. You're just plugging in for the J instead of the I on that one. 3 and 4. Are you brushing your teeth? Thank you.
All right.
No. They're working on these problems on these notes.
Do you have any toothpaste right now, or you just brushing your teeth? Do you have any toothpaste right now, or you just brushing to brush them?
I swallow my spit all the time. You probably don't know this, but every day I was in my math 3 class, I had a dip and I swallowed my spit all the time.
That can't be good for you.
How many of you need that? You say, what am I getting dressed smells like margarine?
Oh.
I'm sorry to disturb the class. I'll never do it again.
That makes me sad a little bit. It does make me a little sad. I found myself like tearing up. That'll make me tear up too. He's making all of his confessions today. Miss Cox today told about how when she had him in class, he peeled an onion and ate it like an apple. All right. Okay. All right. Oh yeah. Aileen refused to. I do not want you to use this exclusively because we need to understand how to set these up and how they work for this. So don't use this exclusively, but I started this by hand and I decided that I didn't really want to add all of those together, so certainly you can pick up your calculator. You also can check your work with these because if you hit F3, what do you see there?
Sigma.
Number 4. And what you'll do is you'll type in the equation. I'm just going to use an x squared, and you'll tell it, comma x, comma 3, comma 7, I think. Is that what you guys got?
Yeah.
Yep. Okay. So, what did you guys get for number 4? 52? We can check that as well if we want. We would have, 6x minus 2, comma x, comma 1, comma 4. Okay, 52 for that is correct. Not really that difficult to do by hand, but a little time consuming if you're trying to do it completely by hand, especially if you have bigger numbers here. Let's talk about some shortcut formulas, okay? Oops.
We don't want to do it. I don't really mind.
Okay, let's look at number 5. We are going to go from 1 to n of 1 over n times k squared plus 1. Yeah, squared. All right, so if we think about doing this problem, okay, I'm going to have 1 over n times 1 squared plus 1. And then I'll have 1 over n times 2 squared plus 1 plus 1 over n times 3 squared plus 1 plus, and then I'm going to keep doing this, and I really don't know what n is, right? But I know that I will end with 1 over n times n squared plus 1. I'm feeling like we're probably still going to have an n in our answer for this, right? So this 1 over n right here is with every single term, correct? So I can factor that out. I can write it out front. In fact, if I wanted to, I could take that 1 over n and I can pull it out before I even start. Because it does not have a k with it. It's not the variable that we're changing. So I could have pulled it out from the very start if I wanted. And then I would have 1 squared plus 1, which would give me 2. 2 squared plus 1, which would give me 5. 3 squared plus 1, which would give me 10. And then, do I need to do that? I don't think so. Then I'll have dot, 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 and we'll have n squared plus 1 for that. So, if I have a problem like this, I don't think if I simplify anything in that. I think I wanted to do, sorry, I'm having a hard time remembering what I think I put this here. To show that 1 over n being pulled out. Let me look at and there must be one like this. Why did I do this? I'm having a hard time remembering my reasons here. That's not on here. Yeah, definitely, for sure.
He said they must be doing everything on top 5.
Must have. I think he's definitely.
Don't worry, I'm not gonna make money.
Yeah. Hunter was not successful in his beta competition. What? Huh?
Yeah, it's like the end of the announcement. All you gotta do is like okay, all wax and take the part and where everything's at and like
Okay, moving on to example 6. All right, so example 6 is a weird question. It asks us to do the sum from 1 to 3 of 5, but there is no variable there. So what's going to happen here is when we plug in 1, we will get 5. And then when we plug in 2, we will get 5 again. And we plug in 3, we will get 5 again. So we will get 15 for that. Okay? So there is a shortcut, obviously, for that. If you just have a constant. Okay? So if C right here is a constant, this is just a number, and I equals 1, it has to be true that I equals 1. If I does not equal 1, you cannot use the shortcut rule. But if I equals 1, then your answer is just going to be that constant times whatever your end value is, right? Because you're going from 1 to 3, that's 3 times. You're adding 5 together 3 times. So like, for example, I don't know if I put an example here, but like if I had the sum from 1 to 8 of 4, what would I get? 32. Right? Because you would just add 4 8 times for that. Okay. You could, yeah. We're pretty much only going to see that index value being 1 for most everything we're going to do, just because it gets more difficult if it isn't. Those are those cases, like we could go into it, but I'm just not going to. So you're pretty much going to see 1 right there, but you could do that if it would start at 2 for that. Okay, so, all right. Okay, so, I think, gosh, I need to go back and refresh my memory on this particular one. I think it was Newton. I think there's a legend about Newton, but there's a chance it was another mathematician. I've got that name wrong. I need to go back and refresh my memory on this. There's sort of a legend that whenever he was a very small child, the teacher asked him to add all of the numbers from 1 to 100. And he did so in seconds and gave the right answer. And the teacher was like, wow, how can you do that so fast? How could you add all of the numbers from 1 to 100 so fast? But I want us to think about how a way that you could do that. Because what the teacher was asking Newton to do, right, was the summation from 1 to 100 of I. Right, that'd be 1 plus 2 plus 3 plus 4 plus 5 all the way up to 100. The way that he thought about this was that this would be 1 plus 2 plus 3 plus dot 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 plus 99 plus 100. And then he thought about, well, what if I wrote that backwards? 100 plus 99. Actually, I need, for the sake of this demonstration, let's put a 98 right there. Plus 98. Plus dot, dot, dot. And then over here it'd be 3, 2, 1. If you wrote them backwards. Okay. Both of those, does it make any difference if you write it backwards? Same value, right? Okay. Now what if we take this and we add them together? So if I add those two together, what will I get when I do 1 plus 100? 101. Right here, what will I get? 101. Here. Dot, dot, dot. Over here. 101. 101. 101. Now, that is not equal to my answer, right? Because that's not equal to my answer, because what I'm really doing is I'm taking this sum and adding it together twice. Right? And so I've got this is like 2 times the sum from 1, I did that, to 100, right? That equals 101, how many times? 100 times, right? Okay? So 2 times the thing that you're looking for would be 10,100. And then what would you have to do? Divide this by 2. And you got 5,050. And as a small child, he thought of this method of figuring it out more quickly on his own without anybody showing it to him. I think it's sort of a legend. I don't know if it's, yeah. I don't know if this is well documented. It's kind of like George Washington and the cherry tree. I don't know if it actually happened or not, but I feel like there's going to be some legends of Coach Wood that live on there in the same way, where nobody knows. Sometimes he tells me things, and I'm like, I don't know if he really did that. That seems too crazy. But I don't know. Who knows if he did it. All right, so let's think about this in a more general sense, because I would like to get a shortcut for this in a more general sense. So let's think about, rather than doing the sum from 1 to 100, let's do 1 to n, so it could be any number, right, of I. Right? So we think about this basically in the same way that we're thinking about our 1 to 100 problem, right? If I'm adding up numbers from 1 to n, I will have 1 plus 2 plus 3 plus ... And then if I want, I know this like last number is going to be n. What would be the number before n? N minus 1. And what would be the number before that? Which would be, in an easier to write way, n minus 2. So if we kind of think about doing the same process with this, right? If I write it again, I'm going to add these together, but I'm going to write these backwards. I would have n plus n minus 1 plus n minus 2 plus ... plus 3 plus 2 plus 1. Right? So when I add those together, here I'll get n plus 1. What do I get when I do 2 plus n minus 1? N plus 1. Right? And here, 3 plus n minus 2. N plus 1. And so on and so forth. Here, I'll get n plus 1, n plus 1, and n plus 1. Right? So what I have done there is I've added this together. I've got twice the sum from 1 to n of I equals n plus 1 all these many times. How many times is that? So I'll have n plus 1. How many times am I adding n plus 1? No, because I got the ... in the middle. It could be 6, but it might not be. N times, right? Because we would go from 1 to n. So it would be n times n plus 1. And then we would divide both sides of this by 2. And it will give you the shortcut that you have down here in that box. This only works if I equals 1, which is pretty much all we're going to look at because it gets too complicated if I does not equal 1. And I don't want to spend our time on that. Just to show you, I've got this written twice on example 7, just to show you there's a couple options. It is not hard to do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, right? But if it is calculator inactive, you got right there 6, that's 10, 15, 21, 28, 36, 45. Right there. So not terribly difficult to do that way, right? But it could also be done this way. 9 times 9 plus 1 divided by 2, which is, of course, 9 times 10 divided by 2, which is 90 divided by 2, which is 45. And I wrote every step there. I probably wouldn't if I was just doing that myself. To me, this is a little easier to do mentally, mental math-wise, if I'm trying to do this without a calculator. Okay, so this is a shortcut rule. There's going to be very little that I give you where I might put one summation problem on the test. I will put the shortcut rules up on the board whenever we do that, because having them all memorized is a little difficult. This one is, I think whenever I first saw the proof for this, that's essentially what I'm doing here, is I'm doing like a mathematical proof to prove this has to be true in all cases. When I first saw the proof of this, I was like, oh, that makes sense. I tell myself, I totally understand that. Now, I would have never came up with it on my own. If I was a young child asked to add 1 to 100, I would just have been like, how fast can I add all these numbers together? And then I would probably still make a mistake. So, but this makes very good sense to me. There are similar proofs for these other two. However, I will hope that you will be happy just to take my word for it, because as you can imagine, it would get much longer for this. So we also have shortcuts for I squared and I cubed, so those are also there as well. So let's talk about what we can do for this, right? So the problem that we did earlier, we went from 1 to n. We had an n left in our answer. One option for this, I'm going to start it, I'm not going to finish it, is I could just do 1 plus 1 over n squared plus 2 plus 1 over n squared plus 3 plus 1 over n squared dot 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 plus 10 plus 1 over n squared. That is an option. You can certainly do it this way. If it is calculator inactive, that is going to take you a very long time to do. You've got to get all of those numbers, add them all together. It's going to take a little while to figure that out. Not impossible, certainly, at all, but it's going to take a little while. Let's look at a few things that we can do with shortcuts that can make this easier. Okay. First of all, anything that is like a scalar multiple that doesn't have the index variable, right? So our index variable in this case is I. That's the number that's changing each time. So that n squared is not changing. It can be pulled out because it's not changing for this. So we can think about this. This is the same as having 1 over n squared times I plus 1, like that. We can just pull that 1 over n squared out front. So we'd have 1 over n squared, the sum from 1 to 10 of I plus 1. We also can break this up. We can do 1 over n squared times the sum from 1 to 10 of I plus, actually we do need a bracket right there because this whole thing is multiplied, and then plus the sum from 1 to 10 of 1. Now, when we do this, we have shortcut rules for both of these summations here. So we're just going to leave our 1 over n squared out front. What was the shortcut rule for the sum from 1 to 10 of I, or 1 to n of I, it was n times n plus 1 over 2, right? That was our shortcut rule for that first. So n is 10 in this case, so you're going to have 10 times 10 plus 1 divided by 2, right there. What was your shortcut rule if you're just adding 1 from 1 to 10? Okay, multiply the number right here by our n, our constant by our n value, so it's just 1 times 10, right? Because this would just be 1 plus 1 plus 1 10 times. Okay, now this will be easier, maybe, anyway, to figure out. It's going to be necessary anyway. For this, we've got, that's going to be 55 plus 10, so we get 65, which this is like on top of the fraction, so we could do 65 over n squared. Now, for this one, you could make an argument on which way is easiest, right? It's not terrible to do this. You'd have 2 and 3 and 4 and 5, and then you would have to add all those numerators together. It's not terrible to just do that one by hand. And as you're doing your homework tonight, if you want to do them by hand and can, go ahead. That's fine. Or you can use shortcut rules, but there are going to be some where shortcut rules are definitely better. I do want you to try to do these without a calculator. You can check your work with a calculator. That will force you to use shortcut rules more than rely on just typing in a bunch of stuff into your calculator, because calculator makes it much easier to add all those things up. Okay, questions here? All right, let's try another one. Okay, here's another example. If I'm not letting you use a calculator, going from 1 to 15 is going to be terrible, right? Because that's a lot of numbers to add together. So, so if I have this, the n can be pulled outside, right? And so it could be written like this: n summation from 1 to 15. Actually, I'm going to do it this way. Let's go ahead and split this up. Of I squared plus the summation from 1 to 15 of negative 1. Or I could have just, actually, let's do it this way. Instead of putting a negative 1 there, let's put a minus in between, and I'll take care of it. I don't like that negative 1 there. You could do it either way. So we've got this where we can now use shortcut rules. So somebody tell me the shortcut rule, because I don't even have these memorized for the I squared. N times n plus 1 plus 2n plus 1 over 6. For this problem, we're plugging in 15 as our n, right? So we'll have 15. 15 times 15 plus 1 times 2 times 15 plus 1 over 6. And if I just have a 1 here, I'm just going to do 15 times 1, right? Just my stop value times the constant that is there. All right, so this is not necessarily easy, but it is a little bit quicker than having to do adding all this out. So I've got 15 times 16 times 31. The n is over here. This is all over 6 minus 15. And let's see, I could reduce this 6 with that 15 and make that, let's see, 3 goes into both of those, so that'd be 5. And that would be 2 if we do that. So then we got to do, let's see, 5 times 16 is 80. Oh, yeah, that's a good idea. Let's do that. So now we got 5 times 8, which is 40. We got to do 40 times 31. Okay, so we got 1240 minus 15 times n, which is going to be 1225 n. Okay, not necessarily simple, but a little bit quicker than trying to do that with a 1, 2, 3, 4, 5, all the way up to 15. There's a reason I'm making you do this. There's a reason for it. All right. One other thing you're going to be asked to do on your assignment is write expressions with sigma notation. So you'll be asked to figure some of them out, and you'll be asked to write some with sigma notation. So if I see 1 plus 2 plus 3 plus blah, dot, 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 plus 6 plus 7, I am adding up. What's my start number? 1. What's my end number? 7. What goes here? Just the I. What about that one?
Sometimes I get bored and I get to rocking my desk and turn it over. You need to do your work. Look, it's done. You just want to add up all the numbers from 1 to 100. So, okay. Yeah. I said add up all the numbers from 1 to 100. What is it? It's like 5,000 feet. Just like it. I said, yeah, it's real easy. I said, you know.
Were you listening outside of my door?
You got 100, and you got 1. You got 99, and you got 2. Right? 98, and you got 3. So what are they all equal? I have 1. How many times are you going to do it? 50.
I must have gotten that wrong. It was not Isaac Newton that was legend. It was about Yeah. I couldn't remember if I was right on who it was. It was you. It wasn't Newton. Yeah.
Those great mathematicians, they're kind of hard to distinguish.
Yeah. Is he listening outside the door? Or did he just see the sum and do it? I don't know. I do not know. Yeah. We need to save that for the record book. Yeah. Yeah. All right. I'd love to see how they're taking him in a few weeks from now. It's possible. You need to get a report. Yeah. Yeah, call them up and be like, how's it going with Coach Ruth up there? He's teaching Algebra 2 all day, I think. All right. So let's look at the next one. Summation, for sure. What number is this going to be starting at? 4. What does it go to? 9. Oh. What is the expression that's being added? I squared plus 1. What you're doing on these is you're looking for that number that changes, right? On those. I think some of these are a little harder to do, like C and D. Because the number that is changing is not quite so obvious for this. What number is changing there? The number on top of the n. That's the number that's changing. Right? So, for this, we would have a summation. We would start with 1. Where would we end? N. And then basically you're going to take the expression that you see, 1 over n times 6 plus, and that I have highlighted that's changing, we're going to change it to our index. That's going to be our I. Therefore that. Okay. What about this last one? Very similar. That numerator right there is changing, right? So, so we would just have from 1 to n, we'd have n times the square root of 1 plus I over n squared. Okay. So this is